In this lecture, we will look at the frequency response of the one-stage op-amp that we have been looking at so far. So, to draw the frequency response, let us first draw the op-amp circuit. So, this is the circuit of the two-stage op-amp. I am going to number the transistors from M0 to M4. Let us assume that the op-amp is being driven differentially. So, I have inputs of plus Vd by 2 and minus Vd by 2. Now, let us assume now that every node of the circuit has some parasitic capacitance. So, we now have 3 nodes in the circuit. I am now going to name them X, Y and Z. And obviously, the parasitic capacitance at these nodes will come from the internal capacitances of the transistors themselves. And once you design the op-amp, you will know what these capacitance values are. For now, we will just assume they are some capacitance Cx, Cy and Cz. Now, what is the effect of Cy? Now, we will note that Cy is actually at small signal ground, and therefore, there is no differential mode current through Cy. And therefore, and of course, this is because both ends of Cy are shorted to small signal ground. So therefore, there is no Cy makes no difference to the differential mode picture. However, Cy affects the common mode gain of the circuit. Clearly, the circuit originally expected a high impedance looking downwards, whereas the minute you have Cy, this impedance will look high for low frequencies, but at higher frequencies, Cy will start presenting smaller and smaller impedances, and therefore the common mode gain, which was originally 0 at very low frequencies, will start getting higher and higher. So, I'll just point out that common mode gain increases at higher frequencies. And finally, the CMRR at high frequencies is degraded. Due to Cy. Now, with that understanding, we will move on to the differential mode picture of the circuit. We will now see the effects of Cx and Cz on the small signal differential mode analysis. So, let us quickly draw the small signal picture. So, this is GM1 times Vd by 2, and I will now express the resistances as their equivalent conductances. So I'm going to call this GDS1. Clearly GDS1 is nothing but 1 over RDS1 and so on. At this node, at node X, we now have 3 impedances connected up. Due to the transistor being due to the drain and gate of transistor M3 being connected, we find that the impedance that M3 presents is now 1 over the conductance that it presents is GM3 plus GDS3. This is due to the feedback action. Now apart from this, you also have a capacitance Cx to ground. The the component, the admittance component of the imaginary component of the admittance is S times Cx. Now this generates a voltage Vx at this node, and this Vx is now applied to the gate of transistor M4, and that causes a small signal current I4. And you also have the component from transistor M2, and this is nothing but the current source I2 is nothing but GM2 times VD by 2 with a negative sign. This conductance is of course GDS2 and this is GDS4. Current I4 is nothing but GM4 times Vx. And finally, you have a capacitance Cz connected between the output node, and this is the output voltage. So now we can start looking at the signal progression through the circuit. So let us first look at the output node. So we can now see that voltage VO is created by these two currents flowing into these three impedances. So we will write VO to be equal to, I am going to call this current I2. It's minus of I2 plus I4. This is the total current flowing into the node times the sum of all the impedances in the node, or it is 1 over sum of all the admittances because they are all in parallel. So that is nothing but GDS2 plus GDS4 plus SCZ. Now it is our job now to find out I2 of S and I4 of S. So let us now write the expression for I2 of S. I2 of S is clearly minus GM2 times VD by 2. And please remember that GM1 is equal to GM2, GDS1 is equal to GDS2, GM3 is equal to GM4, and GDS3 is equal to GDS4. We are assuming that the two transistors on either side of the line of symmetry are identical. Now let us find out what I4 is. To find out I4 is nothing but GM4 times Vx. We now need to find out what Vx is. So I4 is, or I4 of S is GM4 times Vx, and now it is our job to find out Vx of S. Vx of S is clearly equal to this current multiplied by the total impedance at that node with a negative sign. So now I will write this as the negative of GM1 Vd by 2. This is the total current flowing into the node times the sum of all conductances at that node. Over the sum of all conductance at that node. Now the sum of all conductances at that node is of course GM3 plus GDS3 plus GDS1 plus SCX. And since we know that normally GMs are much larger than the corresponding GDSs, I will approximate this to minus GM1 Vd by 2 over GM3 plus SCX. Now finally, we are in a position to write the expression for I4 of S. I4 of S is now GM4 times minus GM1 Vd by 2 over GM3 plus SCX. I am now going to write it in a very specific form. I am going to say this is minus GM1 Vd by 2 over 1 plus SCX over GM3. This is because GM3 is the same as GM4. And now the output voltage VO of S, we have seen that it is minus of I2 plus I4 over GDS2 plus GDS4 plus SCZ. This is clearly GM1 Vd by 2 over one over GDS2 plus GDS4 plus SCZ times 1 plus one over 1 plus SCX over GM3. So finally, VO of S is GM1 Vd by 2 times 2 plus SCX over GM3 by 1 plus SCX over GM3 times GDS2 plus GDS4 plus SCZ. Now I am going to write this in a standard form. I want to rewrite this as VO by Vd of S. So this is the gain of the circuit. I want to write this in a standard form where I have two components. The first component should correspond to the low frequency gain, and the second component should go to 1 at low frequencies, but should contain the poles and zeros of the system. So now let us rewrite this in that specific form. So I am going to take the component GM1 over GDS2 plus GDS4 out of this expression, because this is the low frequency gain of the circuit, and this is going to be the frequency dependent part. So the system has 1 0 at 2 GM3 over Cx, and it has two poles. The first pole is at 1 plus is at GM3 over Cx, and the second pole is at GDS2 plus GDS4 over Cz. So the system has two poles and 1 0. So that is the first thing we will understand. And the second thing to realize is that the positions of the poles and zeros. So omega z is at 2 GM3 over Cx. The first pole omega p1 is at GDS2 plus GDS4 over Cz, and the third pole, the second pole is at GM3 over Cx. Now let us see if these things make sense. So first of all, you can see that GDS2 plus GDS4 is the smallest quantity, and therefore this pole is the closest pole, is the smallest pole, and therefore this is going to be the dominant pole of the system. Now you can see that that dominant pole depends on the output conductance. GDS2 plus GDS4 is the overall output conductance of the system over the total capacitance at Z, which is the sum of the device capacitance and the load capacitance. Omega P2 is the second pole in the system, and that comes about because you have the gate capacitance of M3 and M4 hanging at the common gate terminal. That will be the dominant capacitance at that node. This pole is often called the mirror pole. Now please note that you now have a 0 at twice omega P2. The 0 frequency is at twice omega P2, and first of all you need to ask yourself why you see a 0. Normally you will find that you see a 0 when you look at the transfer function between two paths. If you see a relative phase shift, especially a frequency dependent phase shift between the two paths, you will normally see a 0. So that through the two paths the signal adds destructively at a particular frequency. Do we have these two paths in the system? It turns out that we do. If you actually look at the path traversed by the signal, there are two paths traversed by the signal. In the first path, so the signal from minus Vd by 2 travels directly to the output node. The signal from plus Vd by 2 takes a different path where it sees an extra phase shift due to the presence of Cx, and that is why you see the additional 0 in this path, and it turns out that the frequency of the 0 is at twice the frequency of the